Welcome, friends. I'm so glad you're here, whether you're drifting towards sleep, unwinding after a long day, or simply looking for the quiet companion. You found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet mysteries of Earth's orbital dance through space. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Earth spins through the void, tracing its familiar ellipse around the sun with what appears to be clockwork precision. For most purposes, this orbital dance remains predictable. Sunrise follows sunset. Seasons cycle with gentle reliability, and the planet maintains its steady 93 million mile average distance from our star. Yet beneath this apparent order lies a web of gravitational whispers so complex that even the most sophisticated computers cannot fully capture Earth's orbital future. The illusion of orbital simplicity begins with the Sun's overwhelming gravitational dominance. Our star contains 99.86% of the solar system's mass, creating a gravitational well so deep the Earth cannot escape its pull. This central force follows Newton's inverse square law with mathematical elegance. Twice the distance means 1/4 the gravitational pull. The relationship appears simple, almost elegant in its straightforward geometry. The Earth-Sun system, considered in isolation, produces orbital predictions of stunning accuracy extending millions of years into the future. Only when other bodies enter the calculation does the mathematics begin to fracture into something far more intricate. The solar system contains not just Earth and Sun, but 8 planets, over 200 moons, millions of asteroids, billions of comets, and countless particles of interplanetary dust. Each object, no matter how small, exerts its own gravitational influence on every other object. The cumulative effect creates what mathematicians call the n-body problem, a system of gravitational interactions so complex that no analytical solution exists. Jupiter lurks in the outer solar system, its massive presence creating subtle perturbations that ripple inward toward Earth's orbit. Though separated by hundreds of millions of miles, the gas giant's gravitational field reaches across space with invisible fingers, gently tugging at Earth's trajectory in ways that compound over geological time. These influences measure mere millimeters per year, yet they accumulate across millennia into measurable orbital shifts. Jupiter's orbital period of nearly 12 Earth years creates a gravitational rhythm that pulses through the inner solar system, sometimes reinforcing Earth's orbital characteristics and sometimes opposing them. The mystery deepens when scientists attempt to predict Earth's precise position centuries into the future. Each gravitational calculation requires knowledge of every other body's location, velocity, and mass, creating an interconnected web where uncertainty in one element propagates through the entire system. A small error in measuring Jupiter's position today becomes a larger error in Earth's predicted location tomorrow, and an exponentially larger error in its position next century. This sensitive dependence on initial conditions transforms minor measurement uncertainties into major predictive limitations. Venus and Mercury add their own gravitational voices to the cosmic chorus. Venus, Earth's nearest planetary neighbour, completes its orbit in 225 Earth days, creating a complex pattern of gravitational alignment and opposition that repeats every 584 days. Mercury races around the Sun in just 88 days, its rapid orbital motion creating high-frequency gravitational perturbations that affect Earth's trajectory in subtle but measurable ways. The three inner planets engage in an intricate gravitational dance where each participant influences the others in an endless feedback loop. Even more quietly, the Moon drifts away from Earth at roughly the same rate that fingernails grow, a seemingly trivial 3.8 centimeters per year. This gradual recession alters the Earth-Moon gravitational relationship, subtly modifying our planet's orbital characteristics in ways that unfold over millions of years. The lunar influence that once held Earth's orbit in one configuration slowly weakens, allowing other gravitational voices to speak more loudly in the cosmic conversation. Early in Earth's history, when the Moon orbited much closer, its gravitational influence dominated the planet's orbital evolution. As the Moon retreats, that dominance gradually shifts toward the more distant but massive planets. The Sun itself proves less constant than ancient astronomers assumed. Solar mass decreases by approximately 4.3 million tons per second as nuclear fusion converts matter into energy. This mass loss, though infinitesimal compared to the Sun's total mass, gradually weakens the gravitational force that holds Earth in orbit. The effect allows Earth's orbital radius to expand by about 1.5 centimeters per year, a gentle spiral outward that unfolds over billions of years. The irony emerges slowly. The same fusion process that sustains life on Earth also weakens the gravitational bond that keeps our planet in its life-supporting orbit. Beyond the classical gravitational influences lies the subtle realm of relativistic effects. Einstein's general relativity reveals that massive objects warp the fabric of space-time itself, creating gravitational fields that differ slightly from Newton's predictions. Mercury's orbit precesses by an extra 43 arc-seconds per century due to these relativistic corrections, a tiny deviation that becomes significant when projected across cosmic timescales. Earth experiences similar but smaller relativistic effects that introduce additional uncertainty into long-term orbital calculations. Modern astronomers face the humbling reality that orbital prediction becomes increasingly uncertain as time horizons extend. They can calculate Earth's position next week with extraordinary precision, measuring its location to within centimeters. Next month brings slightly larger uncertainties. Next year introduces meter-scale margins of error, and next century expands those uncertainties to thousands of kilometers. The mathematics of gravitational interaction preserves detailed information about orbital positions for limited time periods before chaos theory takes over and prediction dissolves into statistical probability. The quest for orbital precision reveals a deeper truth about the universe, that even the most fundamental physical processes contain elements of irreducible uncertainty. Earth's orbit appears stable and predictable on human timescales, yet extends into a future where countless gravitational influences will slowly but inevitably alter its path through space. Only the present moment offers true certainty in the gravitational dance that carries our world through the cosmos. The Moon drifts silently away from Earth, its ancient face growing smaller with each passing century, in a recession so gradual that human lifetimes cannot perceive its motion. This lunar retreat unfolds at the glacial pace of continental drift, 3.8 centimeters per year, roughly the speed at which human fingernails grow, yet this seemingly insignificant distance accumulates across geological time into a transformation that fundamentally alters Earth's orbital characteristics and rotational behavior. 4.5 billion years ago, when Earth's surface still glowed with molten rock and the atmosphere consisted of volcanic gases, the Moon orbited much closer to our planet. Recent lunar samples and computer simulations suggest that Luna once hung in Earth's sky at a distance of perhaps 22,000 kilometers, close enough that it would have appeared 14 times larger than today's Moon. and created tides hundreds of meters high. The gravitational forces between Earth and its satellite were correspondingly more intense, locking the two bodies in a tighter orbital embrace that has been slowly unwinding ever since. Tidal friction drives this gradual separation through a process as elegant as it is inexorable. Earth's rotation carries its tidal bulges slightly ahead of the Moon's position, creating a gravitational torque that transfers angular momentum from Earth's spin to Luna's orbital motion. The planet loses rotational energy and slows down, while the Moon gains orbital energy and spirals outward. This energy exchange operates with the patience of geological time, requiring millions of years to produce measurable changes in the Earth-Moon system. The mathematics of tidal recession reveal why the Moon's influence on Earth's orbital prediction becomes increasingly subtle. As Luna moves away, its gravitational effect on Earth weakens according to the inverse square law. Twice the distance produces 1/4 the gravitational influence. The Moon that once dominated Earth's orbital evolution through its powerful nearby presence gradually yields that dominance to the more distant but far more massive planets. Jupiter's gravitational perturbations, once overwhelmed by lunar effects, begin to assert themselves more strongly in Earth's orbital dynamics. Evidence of the Moon's ancient proximity persists in Earth's geological record through fossilized tidal rhythmites, sedimentary layers deposited by ancient tides that recorded the lunar month and Earth's day length across deep time. These stone archives reveal that 620 million years ago, when primitive multicellular life was just beginning to experiment with complex forms, the Moon orbited closer to Earth, and a day lasted only 21.9 hours. The lunar month consisted of just 20 days, creating a calendar utterly foreign to modern experience. Earth spun faster, the Moon loomed larger, and tidal forces sculpted coastlines with far greater intensity than today's gentle oceanic rhythms. The Moon's recession carries profound implications for Earth's long-term orbital stability. Luna's gravitational influence helps stabilize Earth's axial tilt, preventing the chaotic tumbling that might otherwise result from planetary perturbations. Mars, lacking a large stabilizing satellite, experiences axial variations that swing its poles through angles of 60 degrees or more over millions of years. Earth's 23.5-degree tilt remains relatively stable, oscillating only between 22.1 and 24.5 degrees over 41,000-year cycles, largely because the Moon's gravity acts as a cosmic gyroscope that resists changes to our planet's rotational axis. As the Moon continues its outward spiral, this stabilizing influence will gradually weaken. Computer models suggest that in approximately 2 billion years, when the Sun has grown significantly brighter and Earth's oceans have begun to evaporate, the Moon will orbit at roughly 1.6 times its current distance. At that remote epoch, Earth's axial stability will depend more heavily on the gravitational influences of Jupiter and the other giant planets, potentially allowing larger variations in obliquity that could dramatically alter the planet's climate patterns. The recession process itself contains a built-in limit that will eventually halt the Moon's outward journey. Tidal friction not only moves the Moon away from Earth, but also slows our planet's rotation until the day length matches the lunar orbital period. This process, called tidal locking, will eventually synchronize Earth's rotation with the Moon's orbit, creating a situation where the same hemisphere of Earth always faces Luna. When this tidal equilibrium is reached in approximately 50 billion years, long after the Sun has evolved beyond its current state, the Moon will stop receding and begin a slow return journey toward Earth. The irony of lunar recession extends beyond its effects on Earth's orbital dynamics to encompass the very observations that reveal the process. Ancient eclipse records from Babylon, China, and medieval Europe provide precise timing data that allow astronomers to calculate how Earth's rotation has slowed over the past several millennia. Solar eclipses that historical records describe as total would appear partial today because the Moon has moved slightly farther away, reducing its apparent size in Earth's sky. These subtle differences between predicted and observed eclipse paths reveal the Moon's recession with extraordinary precision. Modern laser ranging experiments confirm the Moon's retreat through measurements of stunning accuracy. Since 1969, when Apollo astronauts placed retroreflectors on the lunar surface, scientists have bounced laser beams off these mirrors to measure the Earth-Moon distance with millimeter precision. These experiments not only verify the 8 centimeter annual recession, but also reveal smaller variations in the process caused by Earth's changing rotation rate and the complex dynamics of the Earth-Moon-Sun system. The Moon's gradual departure introduces subtle but measurable uncertainties into Earth's orbital predictions. As Lunar's gravitational influence weakens, Earth becomes more susceptible to perturbations from the planets, particularly Venus and Mars during their closest approaches. The changing Earth-Moon center of mass, called the barycenter, shifts Earth's orbital path in ways that compound over centuries into significant positional uncertainties. What appears as a simple two-body problem today slowly transforms into a more complex gravitational environment, where planetary influences assert themselves with increasing authority. Contemporary lunar recession may be accelerating due to changes in Earth's ocean basins and tidal dissipation patterns. The formation and melting of ice sheets during glacial cycles alters the planet's moment of inertia, affecting its rotation rate and the efficiency of tidal energy transfer. Human activities that modify coastal geography and ocean depths may also influence tidal dissipation, though these effects remain too small to measure with current instruments. The Moon's future recession rate depends on Earth's evolving geophysical characteristics in ways that introduce additional uncertainty into long-term orbital calculations. The story of lunar recession unfolds as a meditation on cosmic patience and the accumulation of infinitesimal changes across vast timescales. Each night, the Moon moves imperceptibly farther from Earth, its gravitational grip weakening by amounts too small for human perception. Yet over the millions of nights that constitute geological time, these minute changes reshape the gravitational architecture of the Earth-Moon system and alter our planet's orbital behavior in ways that even the most sophisticated computer models struggle to predict with perfect accuracy. Jupiter hangs in the outer darkness beyond Mars, a gas giant so massive that it contains more matter than all other planets combined, yet orbits the Sun at a distance where its gravitational influence on Earth seems almost negligible. 500 million miles of space separate the giant planet from our world, a gulf so vast that light takes nearly 3/4 of an hour to cross it. Yet across this cosmic void, Jupiter's immense gravitational field reaches toward Earth with invisible persistence, creating subtle orbital perturbations that accumulate over millennia into significant deviations from predicted paths. The scale of Jupiter's mass defies easy comprehension, with 318 times Earth's mass compressed into its swirling atmosphere and metallic hydrogen core. Jupiter warps space-time around itself in ways that affect every object in the solar system. The planet's gravitational field is so powerful that it captures asteroids into complex orbital resonances, shepherds the asteroid belt into its current configuration, and deflects incoming comets in trajectories that sometimes send them careening toward the inner planets or fling them entirely out of the solar system. This gravitational influence operates through mechanisms both direct and indirect, creating a web of perturbations that complicate Earth's orbital predictions in ways that emerge slowly over extended time periods. Jupiter's 11.86-year orbital period creates a gravitational rhythm that pulses through the inner solar system, sometimes reinforcing Earth's orbital characteristics and sometimes opposing them. When Jupiter and Earth align on the same side of the Sun, their combined gravitational pull subtly affects the entire solar system's center of mass, creating perturbations that ripple through planetary orbits for decades. The mathematics of Jupiter's influence involve what astronomers call secular perturbations, long-term changes in orbital elements that unfold over thousands or millions of years rather than the short-term variations visible from year to year. These secular effects alter Earth's orbital eccentricity, the shape parameter that describes how elliptical rather than circular our planet's path appears, over roughly 100,000-year cycles. Jupiter's gravitational influence causes Earth's orbital eccentricity to vary between 0.000055 and 0.0679, transforming our planet's path from nearly circular to noticeably elliptical and back again. The irony of Jupiter's influence lies in its dual nature as both stabilizer and perturber of inner planet orbits. Computer simulations suggest that without Jupiter's massive presence, Earth's orbit would be far less stable over geological timescales. The gas giant acts as a gravitational shield, deflecting many asteroids and comets away from the inner solar system before they can impact Earth or the other terrestrial planets. Yet this same protective influence creates the orbital perturbations that make Earth's precise future position impossible to predict beyond certain time horizons. Recent research reveals that Jupiter's orbit itself undergoes slow changes that affect its gravitational influence on Earth in complex ways. The giant planet participates in gravitational resonances with Saturn that cause both planets' orbits to evolve over millions of years. These slow orbital changes alter the strength and timing of Jupiter's perturbations on Earth's orbit, introducing additional layers of uncertainty into long-term predictions. What appears as a stable gravitational influence today slowly shifts in ways that compound the difficulty of orbital forecasting. The Nice model of solar system evolution suggests that Jupiter and the other giant planets migrated inward and then outward during the solar system's first billion years, fundamentally restructuring the architecture of planetary orbits. Evidence for this migration appears in the current orbital configuration of the outer planets and the distribution of objects in the Kuiper belt beyond Neptune. If such large-scale orbital migration occurred in the past, it raises questions about the long-term stability of current planetary positions and the possibility of future orbital evolution driven by gravitational interactions among the giant planets. Jupiter's gravitational field creates resonance effects that demonstrate how small periodic forces can produce large cumulative changes over extended time periods. The Kirkwood gaps in the asteroid belt mark orbital distances where asteroids experience gravitational resonances with Jupiter, locations where the asteroid orbital period forms simple ratios like 3, 1 or 2, 1 with Jupiter's 12-year orbit. At these resonance locations, Jupiter's repeated gravitational tugs occur at the same point in the asteroid's orbit, gradually building up perturbations that eventually eject the asteroid from its original path. Earth experiences similar but much weaker resonance effects from Jupiter's gravitational field. These resonances operate over much longer timescales than the asteroid belt interactions, requiring millions of years to produce measurable orbital changes. The complexity arises because Earth simultaneously experiences resonance effects from multiple planets, not just Jupiter but also Venus, Mars, and the other giant planets, creating overlapping patterns of gravitational influence that interact in ways too complex for analytical solutions. Modern computational methods reveal the chaotic nature of Jupiter's long-term gravitational influence on Earth's orbit. Small uncertainties in Jupiter's current position and velocity propagate through gravitational calculations to create exponentially growing uncertainties in Earth's predicted future orbit. This sensitive dependence on initial conditions means that tiny measurement errors in Jupiter's orbital parameters today translate into enormous uncertainties in Earth's orbital position millions of years from now. The challenge of predicting Jupiter's own orbital evolution compounds the difficulty of forecasting its influence on Earth. The gas giant participates in a complex gravitational dance with Saturn, Uranus, and Neptune that creates chaotic dynamics in the outer solar system. These interactions unfold over time, scales of millions to hundreds of millions of years, making Jupiter's future orbital parameters uncertain and therefore making its future influence on Earth impossible to calculate with perfect precision. Observational evidence for Jupiter's perturbations of Earth's orbit appears in subtle variations in our planet's distance from the Sun and the timing of seasonal changes. No, these variations, measured through precise astronomical observations and analysis of paleoclimatic records, reveal the fingerprint of Jupiter's gravitational influence operating across geological timescales. Ice core data and sedimentary records preserve evidence of climate cycles that correlate with calculated periods of Jovian orbital influence, providing empirical confirmation of the gas giant's role in Earth's long-term orbital evolution. The study of Jupiter's gravitational effects on Earth illuminates a fundamental tension in orbital mechanics between apparent stability and underlying chaos. Earth's orbit remains stable enough to maintain relatively constant climatic conditions over geological time, yet sensitive enough to Jupiter's distant influence that long-term orbital prediction becomes impossible. This paradox reflects the nature of gravitational systems where apparently stable configurations contain seeds of unpredictability that emerge only when viewed across sufficiently extended time horizons. Jupiter continues its stately progress around the Sun, its massive presence creating gravitational currents that flow through the solar system with patient persistence. Each orbit of the giant planet shifts the gravitational landscape slightly, altering the subtle forces that guide Earth's path through space in ways too small for immediate detection but large enough to accumulate across cosmic time into orbital changes that reshape our planet's relationship with the Sun. The Sun breathes across space in a continuous exhalation of charged particles and electromagnetic radiation, creating what scientists call the solar wind, a stream of protons and electrons that flows outward from our star at speeds exceeding 1 million miles per hour. This invisible river of solar matter carries with it magnetic field lines that stretch across the solar system, creating a dynamic environment where electromagnetic forces interact with gravitational dynamics in ways that subtly influence planetary orbits over extended time periods. Solar wind particles strike Earth's magnetosphere with pressures measured in mere billionths of atmospheric pressure at sea level. Yet these seemingly negligible forces accumulate over geological time into measurable orbital effects. The magnetosphere, Earth's protective magnetic bubble, deflects most solar wind particles around the planet, but the interaction creates a bow shock wave that experiences constant pressure from the flowing solar plasma. This pressure varies with solar activity cycles, creating oscillating forces that push against Earth's magnetic field and subtly affect the planet's orbital velocity. Radiation pressure from sunlight itself contributes additional forces that perturb Earth's orbital motion in ways too small for casual detection, but significant enough to appear in precision, astronomical calculations. Each photon of sunlight carries momentum that transfers to any object it strikes, creating a gentle but persistent push away from the Sun. For Earth, With its massive bulk and relatively small cross-sectional area, radiation pressure effects remain minimal, yet over millions of years, even these minute forces contribute to the cumulative uncertainty that makes long-term orbital prediction impossible. The solar wind exhibits dramatic variations that correlate with the Sun's magnetic activity cycles, most prominently the 11-year sunspot cycle that alternates between solar maximum and minimum conditions. During solar maximum, when the Sun's magnetic field becomes highly twisted and unstable, solar wind intensity can increase by factors of 10 or more above quiet conditions. Coronal mass ejections, massive eruptions of solar plasma, can accelerate billions of tons of charged particles to speeds approaching 3 million miles per hour, creating shock waves that propagate throughout the solar system. These variations in solar wind intensity create corresponding changes in the electromagnetic forces acting on Earth and other planets. During periods of high solar activity, increased radiation pressure and particle bombardment create slightly stronger forces that tend to push planets away from the Sun. During solar minimum conditions, when the solar wind weakens to its quietest levels, these outward forces diminish correspondingly. The net effect introduces small but measurable variations in planetary orbital velocities that compound over centuries into significant uncertainties in orbital position calculations. Historical records of solar activity, preserved in ice cores, tree rings, and other paleoclimatic archives, reveal that the Sun's electromagnetic output has varied significantly over time, scales ranging from years to millennia. The Maunder minimum, a period of reduced solar activity between 1645 and 1715, coincided with unusually cold temperatures across Europe and North America, demonstrating the Sun's variable influence on Earth's climate system. Less obvious but equally real are the orbital perturbations that such long-term solar variations create through their effects on radiation pressure and electromagnetic forces. The interaction between solar wind and planetary magnetospheres creates additional complications for orbital prediction through processes that couple electromagnetic and gravitational effects in complex ways. Earth's magnetic field channels some solar wind particles into the polar regions, where they create aurora displays and deposit energy into the upper atmosphere. This energy deposition affects atmospheric density at satellite altitudes, creating drag forces that slowly alter the orbits of artificial satellites and contribute to atmospheric escape processes that gradually reduce Earth's mass. Atmospheric escape, driven partly by solar wind interactions with Earth's upper atmosphere, removes approximately 3 kilograms of atmospheric mass per second from our planet. This mass loss, though infinitesimal compared to Earth's total mass, gradually reduces the gravitational forces in the Earth-Moon system and affects long-term orbital evolution. The rate of atmospheric escape depends on solar activity levels, creating another link between solar variability and orbital dynamics that unfolds over geological timescales. The solar wind carries with it the Sun's magnetic field in a configuration called the interplanetary magnetic field, which extends throughout the solar system and influences the motion of charged particles around all the planets. This magnetic field undergoes reversals and reconfigurations that correlate with solar activity cycles, creating time-varying electromagnetic environments that affect satellite orbits and potentially influence long-term planetary orbital evolution through subtle electromagnetic forces. Precision measurements of solar wind properties reveal additional complexities that contribute to orbital prediction difficulties. The solar wind exhibits turbulence, shock waves, and magnetic field discontinuities that create irregular variations in the forces acting on planetary magnetospheres. These irregularities occur on timescales ranging from minutes to years, creating a spectrum of perturbations that interact with orbital mechanics in ways too complex for complete theoretical modeling. The heliosphere, The vast bubble of solar wind that surrounds the entire solar system creates a boundary condition that affects the gravitational environment through its interaction with interstellar space. The heliopause, where solar wind meets the interstellar medium, lies roughly 120 astronomical units from the Sun, far beyond the orbits of all known planets. Yet this boundary influences the distribution of cosmic rays and interstellar particles that enter the solar system, creating subtle variations in the local gravitational environment that may affect long-term orbital stability. Recent space missions, including the Voyager probes and the Parker Solar Probe, reveal that the solar wind environment exhibits far more complexity and variability than early theoretical models suggested. The solar wind speed, density, temperature, and magnetic field strength all vary continuously, creating a dynamic electromagnetic environment that influences planetary orbits through mechanisms still being discovered and quantified by solar physicists and orbital dynamicists. The solar wind's influence on orbital prediction extends beyond direct electromagnetic forces to include its effects on space debris and micrometeorite populations that create additional perturbations on planetary motion. Solar wind pressure affects the orbits of small particles throughout the solar system, altering the distribution of dust and debris that planets encounter in their orbital paths. These encounters, while individually insignificant, accumulate over geological time into measurable changes in planetary masses and orbital characteristics. Solar storms, intense bursts of solar wind and electromagnetic radiation, can temporarily overwhelm planetary magnetospheres and create dramatic increases in the electromagnetic forces acting on orbital bodies. The largest recorded solar storm. The Carrington event of 1859 created aurora displays visible as far south as the Caribbean and induced electrical currents strong enough to disrupt telegraph systems worldwide. Such events, occurring perhaps once per century on average, create temporary but significant perturbations in the electromagnetic environment that affects orbital dynamics. The challenge of incorporating solar wind effects into orbital predictions reflects the broader difficulty of coupling electromagnetic and gravitational physics across the vast range of time and distance scales relevant to planetary motion. Solar wind variations occur on timescales of minutes to decades, while their cumulative orbital effects unfold over centuries to millennia. This separation of timescales makes it difficult to connect observed solar variability with measured changes in planetary orbits. Yet the connection undoubtedly exists and contributes to the fundamental unpredictability of long-term orbital evolution. Modern computational models attempt to include solar wind effects in orbital calculations, but the complexity of the coupled electromagnetic gravitational system requires approximations and simplifications that introduce additional uncertainties into predictions. The solar wind environment itself remains partially unpredictable, particularly during periods of high solar activity when the Sun's magnetic field undergoes rapid and chaotic changes that affect solar wind properties in ways too complex for complete theoretical modelling. The Sun continues its steady nuclear burning, converting 4 million tons of matter into energy each second, while simultaneously exhaling the solar wind that carries solar material throughout the planetary system. This dual process, energy generation and mass loss, creates the electromagnetic environment in which Earth's orbital motion unfolds, adding layers of complexity to gravitational dynamics that ensure the impossibility of perfect long-term orbital prediction, even as they maintain the broader stability that allows life to persist on our slowly wandering world. Between Mars and Jupiter lies a vast region of space populated by millions of rocky fragments, the asteroid belt, a cosmic debris field that stretches across nearly 200 million miles of the solar system's middle distance. These remnants of planetary formation, ranging in size from grain-sized particles to objects hundreds of kilometers across, create a complex gravitational environment where resonance effects and orbital interactions contribute subtle but persistent perturbations to Earth's orbital motion over geological timescales. The asteroid belt contains perhaps 2 million objects larger than 1 kilometer in diameter, with a total mass roughly equivalent to 4% of Earth's moon. This distributed mass creates gravitational influences that, while individually negligible, collectively contribute to the complex web of forces that make precise long-term orbital prediction impossible. Each asteroid follows its own elliptical path around the Sun, and the combined gravitational effects of these millions of orbiting bodies create small perturbations that ripple through the inner solar system. Ceres, the largest asteroid and the only dwarf planet in the asteroid belt, contains approximately 1/3 of the belt's total mass within its 940-kilometer diameter. This substantial concentration of matter creates gravitational effects measurable enough to appear in precision calculations of planetary motion. Ceres completes its orbit around the Sun every 6 Earth years, creating a gravitational rhythm that subtly influences the orbits of nearby asteroids and contributes to the long-term perturbations that affect Earth's orbital evolution. The distribution of asteroids throughout the belt follows patterns shaped by gravitational resonances with Jupiter, creating a complex structure of gaps and concentrations that astronomers call Kirkwood gaps. These gaps occur at orbital distances where asteroid periods form simple mathematical ratios with Jupiter's 11.86-year orbit, locations where the gas giant's repeated gravitational tugs gradually remove asteroids over millions of years. The resulting structure creates a non-uniform gravitational field that varies with position and contributes to the irregular perturbations experienced by objects passing through or near the asteroid belt region. Asteroid families, groups of objects that share similar orbital characteristics and likely originated from the collision and fragmentation of larger parent bodies, create clusters of gravitational influence that change the local gravitational environment in ways that affect long-term orbital stability. The Flora family, containing over 13,000 known asteroids in the inner belt, creates a concentration of gravitational influence that affects the motion of Mars and contributes indirectly to Earth's orbital perturbations through the complex chain of gravitational interactions that connects all solar system bodies. The Trojan asteroids, captured in Jupiter's gravitational influence at the stable Lagrange points that lead and follow the giant planet in its orbit, create additional gravitational concentrations that affect the outer solar system's dynamics. These asteroid populations, numbering in the hundreds of thousands, orbit in gravitational harmony with Jupiter while creating small but measurable perturbations that influence the orbital evolution of the gas giant itself and thereby affect Jupiter's long-term influence on Earth's orbital motion. Recent discoveries reveal that asteroid orbits exhibit chaotic behavior over million-year timescales, with small gravitational perturbations from planets causing some asteroids to migrate between different regions of the solar system. These orbital migrations alter the mass distribution within the asteroid belt and change the gravitational influences acting on planetary orbits in ways that contribute to the unpredictability of long-term orbital evolution. Computer simulations suggest that roughly 20% of asteroids will experience significant orbital changes over 100 million year periods. The Yarkovsky effect, a subtle force created when rotating asteroids absorb sunlight and re-radiate thermal energy, causes gradual orbital evolution for smaller asteroid belt objects that indirectly affects the gravitational environment experienced by larger bodies. This thermal force, operating over millions of years, can migrate asteroids across significant orbital distances and alter the mass distribution within the belt in ways that change the collective gravitational influence of asteroid populations on planetary motion. Near-Earth asteroids, objects whose orbits bring them close to Earth's path around the Sun, create more direct gravitational influences that contribute to orbital prediction uncertainties. These objects, numbering in the tens of thousands, periodically approach Earth at distances close enough that their gravitational effects become temporarily significant. During close approaches, even relatively small asteroids can create measurable perturbations in Earth's orbital velocity that contribute to the cumulative uncertainties in long-term position calculations. The discovery rate of new asteroids continues to accelerate with improved telescopic surveys, revealing that the asteroid population contains far more objects than earlier estimates suggested. Each newly discovered asteroid adds another gravitational influence to the complex calculation required for precise orbital prediction, demonstrating that even comprehensive catalogues of solar system objects remain incomplete enough to affect the accuracy of long-term orbital forecasts. Asteroid collisions, occurring perhaps once per million years for kilometer-sized objects, create sudden changes in the mass distribution within the belt that affect the local gravitational environment. These collision events can fragment large asteroids into multiple smaller objects, creating new gravitational influences while removing others. The unpredictable timing and outcomes of such collisions introduce additional elements of uncertainty into long-term orbital calculations that extend beyond the purely gravitational perturbations of intact objects. The gravitational influence of asteroid belt objects on Earth's orbit operates primarily through their collective effect on Mars, whose orbit lies adjacent to the inner edge of the asteroid belt. Mars experiences more direct gravitational perturbations from belt objects than Earth, and these Martian orbital changes propagate through gravitational interactions to affect Earth's orbital evolution over extended time periods. This indirect coupling demonstrates how gravitational influences can propagate through the solar system in complex chains of cause and effect. Secular resonances, long-term gravitational interactions between asteroid orbital frequencies and planetary motion, create additional complications for orbital prediction by linking asteroid belt dynamics with planetary orbital evolution. These resonances operate over time scales of millions of years and can cause asteroids to experience large changes in orbital eccentricity or inclination that alter their gravitational influences on planetary motion. The chaotic nature of these resonance interactions makes their long-term evolution impossible to predict with perfect accuracy. Modern computational models of solar system dynamics must include the gravitational effects of hundreds of thousands of known asteroids to achieve the highest accuracy in orbital predictions. Yet even these comprehensive models remain incomplete due to the millions of smaller objects that remain undetected. Each additional asteroid included in calculations improves prediction accuracy in the short term, while revealing new sources of uncertainty that limit long-term predictability. The asteroid belt represents a microcosm of the challenges facing orbital prediction, a region where millions of individual gravitational influences combine to create collective effects that shape planetary motion over geological timescales. The complex interactions between asteroids, their resonances with planetary motion, and their own chaotic orbital evolution ensure that perfect prediction of their future gravitational influences remains impossible, contributing another layer of uncertainty to the already complex problem of forecasting Earth's orbital future. The rocky debris continues its ancient dance around the Sun, each fragment following gravitational laws with perfect precision, while participating in a collective motion too complex for complete prediction. The asteroid belt stands as a testament to the accumulated complexity that emerges when millions of gravitational influences combine across the vast timescales of planetary motion, creating patterns beautiful in their mathematical structure yet ultimately unpredictable in their detailed evolution. Venus and Mercury trace their swift orbits closer to the Sun than Earth, creating a gravitational duet in the inner solar system that demonstrates the mathematical complexity of multi-body orbital interactions. These two worlds, locked in their own elliptical dances around our star, exert gravitational influences on Earth that vary with their changing positions in ways that create what mathematicians call the three-body problem, a system of gravitational interactions with no analytical solution and behavior that becomes chaotic over extended time periods. Mercury, the innermost planet, completes its orbit in just 88 Earth days, racing around the Sun at average speeds of 47 kilometers per second. This rapid motion creates high-frequency gravitational perturbations that affect Earth's orbit through subtle but measurable influences that compound over centuries. Mercury's highly eccentric orbit, the most elliptical of any planet, causes its distance from the Sun to vary between 46 million and 70 million kilometers, creating corresponding variations in its gravitational influence on the other inner planets. Venus maintains a nearly circular orbit at 108 million kilometers from the Sun, completing its journey in 225 Earth days. The planet's proximity to Earth and substantial mass, roughly 82% of Earth's mass, make it the second strongest gravitational influence on our planet after the Moon. Venus approaches within 25 million miles of Earth every 584 days during inferior conjunction, creating periodic gravitational perturbations that temporarily accelerate or decelerate our planet's orbital motion by measurable amounts. The mathematical complexity of inner-planet interactions emerges from the fact that each world simultaneously influences the others in an endless feedback loop. Earth's gravitational field affects both Venus and Mercury, altering their orbits in ways that change their future gravitational influences on Earth. These interactions create what chaos theorists call sensitive dependence on initial conditions. Small uncertainties in current planetary positions amplify exponentially over time, making long-term orbital prediction impossible despite the mathematical precision of gravitational laws. Venus and Earth participate in a gravitational resonance that creates a regular pattern of close approaches repeating every 8 Earth years, during which Venus completes exactly 13 orbits while Earth completes 8. This 8-13 resonance creates a 5-petaled flower pattern when the two planets' positions are plotted relative to each other, demonstrating how gravitational interactions can create beautiful mathematical structures even as they introduce chaos into long-term orbital evolution. The gravitational perturbations from Venus and Mercury operate on multiple timescales simultaneously, creating overlapping cycles of influence that interact in complex ways. Short-period perturbations occur during close planetary approaches and affect orbital velocity on timescales of days to months. Medium-period effects unfold over years to decades as orbital alignments shift, while long-period secular variations require centuries to millennia to complete their cycles. Mercury's orbit itself exhibits chaotic behavior over time, scales of millions of years, with computer simulations revealing that the planet's orbital eccentricity undergoes irregular variations that can occasionally bring it close enough to Venus for significant gravitational encounters. These potential close approaches introduce additional uncertainty into Mercury's long-term orbital evolution and therefore into its future gravitational influence on Earth's orbital motion. The challenge of predicting Venus's orbital influence on Earth extends beyond pure gravitational calculations to include the effects of atmospheric mass loss and planetary evolution. Venus loses atmospheric material to space through solar wind interactions at rates that gradually reduce the planet's mass over geological time. This slow mass loss weakens Venus's gravitational influence on Earth in ways that unfold over billions of years, contributing to the long-term unpredictability of inner planet orbital dynamics. Relativistic effects become particularly important for Mercury due to its proximity to the Sun and high orbital velocity. Einstein's general relativity predicts that Mercury's orbit should precess by an additional 43 arcseconds per century beyond Newtonian gravitational effects, a prediction confirmed by precise astronomical observations. These relativistic corrections affect Mercury's long-term orbital evolution and therefore its gravitational influence on the other inner planets in ways that pure Newtonian mechanics cannot fully capture. The three-body interactions among Venus, Earth, and Mercury create scenarios where small changes in one planet's orbit can produce large changes in the others through gravitational amplification effects. Computer studies reveal that uncertainties in Mercury's current position of just 1 kilometer can grow to uncertainties of millions of kilometers in Earth's predicted position after 100 million years, demonstrating the fundamental limitations of long-term orbital prediction, even with perfect knowledge of gravitational physics. Venus exhibits the most circular orbit of any planet, with an eccentricity of just 0.007, yet even this near-circular path undergoes slow variations driven by gravitational perturbations from Earth, Mercury, and the outer planets. These variations in Venus's orbital shape create corresponding changes in its gravitational influence on Earth that contribute to the secular perturbations affecting our planet's orbital evolution over geological timescales. The historical record of Venus and Mercury observations reveals subtle changes in their orbital timing that confirm the reality of gravitational perturbations predicted by celestial mechanics. Ancient Babylonian astronomical records, extending back over 2,500 years, show small but measurable deviations from simple elliptical motion that match modern calculations of planetary perturbations, providing empirical validation of the complex gravitational interactions that make perfect orbital prediction impossible. Modern space missions to Venus and Mercury provide increasingly precise measurements of these planets' masses, orbital parameters, and internal structures that improve the accuracy of gravitational calculations while revealing new sources of uncertainty. The Messenger mission to Mercury discovered that the planet's core is larger than previously thought, affecting calculations of its gravitational field and therefore its influence on the other inner planets. The interaction between Venus and Earth's orbits creates climate effects on both worlds through gravitational influences on orbital eccentricity and obliquity. Venus's gravitational perturbations contribute to the slow variations in Earth's orbital shape that help drive ice age cycles over hundreds of thousands of years. Similarly, Earth's gravitational influence on Venus may contribute to that planet's remarkably slow rotation, which takes 243 Earth days to complete one spin. The inner planets continue their intricate gravitational ballet around the Sun, each world following the laws of physics with mathematical precision while participating in interactions too complex for perfect prediction. Venus and Mercury orbit closer to our star's powerful gravitational influence, yet their combined effects on Earth demonstrate how even the most fundamental physical processes contain elements of irreducible uncertainty that emerge when multiple gravitational influences combine across the vast timescales of planetary evolution. Einstein's general theory of relativity reveals that massive objects warp the fabric of space-time itself, creating gravitational fields that differ subtly but measurably from Newton's inverse square law predictions. These relativistic corrections to classical orbital mechanics introduce small but persistent deviations in planetary motion that accumulate over geological timescales, adding another layer of complexity to the already challenging problem of long-term orbital prediction. The curvature of space-time around the Sun creates orbital precession effects that cause planetary orbits to slowly rotate in space, rather than repeating exactly the same elliptical paths. Mercury, orbiting closest to the Sun where space-time curvature reaches its maximum intensity in the solar system, experiences the strongest relativistic effects with its orbit, precessing by an additional 43 arcseconds per century beyond what Newtonian gravity predicts. This seemingly tiny deviation, less than 0.012 degrees per century, accumulates over millions of years into substantial changes in Mercury's orbital orientation. Earth experiences similar but weaker relativistic precession due to its greater distance from the Sun, where space-time curvature diminishes according to the inverse square of distance. The relativistic contribution to Earth's orbital precession amounts to approximately 3.8 arcseconds per century, a deviation so small that it remained undetectable until precision astronomical observations achieved sufficient accuracy in the late 20th century. Yet this minute effect compounds over geological timescales into orbital changes that affect Earth's relationship with the Sun in ways that pure Newtonian mechanics cannot predict. General relativity also predicts gravitational time dilation effects that subtly influence orbital dynamics through their impact on the fundamental measurement of time itself. Clocks closer to massive objects run slower relative to clocks in weaker gravitational fields, creating a time dilation gradient that affects the rate at which orbital processes unfold. Near Earth's surface, gravitational time dilation causes clocks to run approximately 22 microseconds per year slower than identical clocks in deep space, a difference that modern precision requires GPS satellites to correct continuously. The relativistic effect known as frame dragging, caused by the rotation of massive objects, creates additional perturbations in orbital motion that contribute to long-term unpredictability. Earth's rotation drags space-time around with it, creating a gravitomagnetic field that affects the orbits of satellites and other nearby objects. This effect, measured by the Gravity Probe B mission, influences the precession of Earth's own orbit around the Sun through subtle interactions between Earth's rotational frame dragging and the Sun's space-time curvature. Gravitational waves, ripples in space-time itself created by accelerating massive objects, represent another relativistic effect that influences orbital evolution over extremely long timescales. Binary star systems lose orbital energy through gravitational wave radiation, causing their orbits to decay and the stars to spiral closer together, while Earth's orbital motion around the Sun generates gravitational waves too weak to cause measurable orbital decay over the age of the solar system. These waves do carry away infinitesimal amounts of orbital energy that contribute to the theoretical impossibility of perfect long-term orbital prediction. The post-Newtonian approximation used in modern orbital calculations includes multiple orders of relativistic corrections that become increasingly important for high-precision applications. First-order corrections account for the basic space-time curvature effects, while second-order terms include gravitomagnetic influences and velocity-dependent effects. Third-order corrections involve gravitational wave emission and other subtle relativistic phenomena that affect orbital motion at levels approaching current measurement precision. Modern tests of general relativity using planetary motion provide some of the most stringent confirmations of Einstein's theory, while simultaneously revealing the limits of orbital predictability. The Cassini spacecraft's radio signals, tracked with extraordinary precision as they passed near the Sun, confirmed relativistic time delay effects, predicted by general relativity to within 0.002% accuracy. These same measurements reveal that even tiny uncertainties in relativistic parameters translate into significant uncertainties in long-term orbital predictions. The equivalence principle, the fundamental insight that gravitational and inertial forces are locally indistinguishable, underlies all relativistic corrections to orbital mechanics while introducing conceptual challenges for long-term prediction. Local space-time curvature depends on the distribution of matter and energy throughout the universe, creating subtle connections between Earth's orbital motion and the cosmic environment that extend far beyond the solar system's gravitational influences. Relativistic effects couple with classical gravitational perturbations in ways that amplify uncertainties in orbital prediction through non-linear feedback mechanisms. Small relativistic corrections to planetary positions alter the gravitational forces between planets, which in turn affects the relativistic corrections in a complex interplay between classical and modern physics. These coupled effects make it impossible to separate relativistic and Newtonian influences in long-term orbital evolution calculations. The search for additional relativistic effects in planetary motion continues to push the boundaries of both theoretical physics and observational astronomy. Proposed modifications to general relativity, motivated by dark matter and dark energy observations, predict subtle deviations from Einstein's theory that might appear in precision measurements of planetary orbits. Current observational limits constrain such deviations to levels smaller than existing relativistic effects. Yet future precision improvements may reveal new physics through orbital motion analysis. Relativistic effects in orbital mechanics demonstrate how even the most successful physical theories contain elements of uncertainty that limit long-term predictability. General relativity has passed every experimental test with remarkable precision. Yet the theory's predictions for planetary motion involve mathematical calculations so complex that numerical approximations introduce unavoidable errors that grow over extended time periods. The measurement of relativistic orbital effects requires atomic clocks, laser interferometry, and other precision technologies that approach the fundamental limits imposed by quantum mechanics. These quantum limits introduce another layer of uncertainty into relativistic orbital calculations, connecting the macroscopic motion of planets with the microscopic uncertainties that govern all physical measurements at the most fundamental level. Einstein's insight that gravity represents the curvature of space-time itself transforms orbital prediction from a purely classical problem into one that bridges multiple areas of modern physics. The relativistic corrections to planetary motion serve as a reminder that even the most familiar and apparently predictable phenomena, the motion of Earth around the Sun, contains subtle connections to the deepest mysteries of space, time, and the fundamental structure of physical reality. Earth spins through space not as a perfect sphere but as an oblate ellipsoid, flattened at the poles and bulging at the equator due to rotational forces that have shaped our planet's form over billions of years. This departure from spherical symmetry creates gravitational complexities that affect Earth's orbital motion in ways that compound the already challenging problem of long-term orbital prediction. The equatorial bulge, measuring approximately 21 kilometers in radius difference between Earth's equatorial and polar dimensions, arises from the planet's 24-hour rotation period, which creates centrifugal forces that push material away from the rotation axis. This redistribution of mass creates what geophysicists call Earth's quadrupole moment, a mathematical description of how the planet's gravitational field deviates from that of a perfect sphere. The resulting gravitational field affects the motion of nearby objects, including the Moon, and creates subtle feedback effects that influence Earth's orbital evolution. Earth's internal structure adds additional complexity to its gravitational field through density variations that reflect the planet's layered composition and thermal state. The solid inner core, liquid outer core, solid mantle, and thin crust each contribute differently to the overall mass distribution, creating gravitational anomalies that vary with position around the planet. These internal mass variations affect Earth's rotational dynamics and therefore its orbital characteristics through conservation of angular momentum. The planet's mass distribution changes continuously through geological processes that operate on timescales ranging from seconds to millions of years. Tectonic plate motion redistributes surface material. Volcanic eruptions transfer mass from Earth's interior to its surface, and erosion moves material from continents to ocean basins. Each of these processes alters Earth's moment of inertia and affects its rotational behavior in ways that couple with orbital dynamics through tidal forces and gravitational interactions with other solar system bodies. Glacial cycles create particularly dramatic changes in Earth's mass distribution as ice sheets advance and retreat across continental surfaces. During ice ages, billions of tons of water move from oceans to continental ice sheets, creating load changes that deform Earth's crust and alter the planet's rotational characteristics. The end of the last ice age, roughly 12,000 years ago, initiated crustal rebound processes that continue today, gradually redistributing mass in ways that affect Earth's rotation rate and orbital coupling with the Moon. Modern satellite measurements reveal that Earth's gravitational field exhibits small but measurable variations that change with time due to mass redistribution processes in the atmosphere, oceans, and solid Earth. The GRACE satellite mission detects these gravitational changes with sufficient precision to monitor groundwater depletion, ice sheet melting, and other mass transfer processes that affect Earth's rotational dynamics. These measurements demonstrate that Earth's gravitational field remains dynamic on timescales relevant to orbital prediction. Ocean tides, driven by lunar and solar gravitational forces, create periodic redistribution of water mass that affects Earth's rotational dynamics through changes in the planet's moment of inertia. The twice-daily tidal cycle transfers rotational energy between Earth's solid body and its fluid envelopes, gradually slowing the planet's rotation while affecting the efficiency of tidal energy dissipation that drives lunar recession. These tidal effects couple Earth's changing shape with its orbital evolution in ways that introduce additional complexity into long-term orbital calculations. Atmospheric mass redistribution through seasonal weather patterns, monsoon cycles, and long-term climate variations also affects Earth's rotational dynamics and therefore its orbital characteristics. The transfer of water vapor between oceans and continents, the seasonal advance and retreat of snow cover, and the growth and decay of atmospheric pressure systems all contribute to small but measurable changes in Earth's rotation rate that couple with orbital mechanics through tidal forces and gravitational interactions. Earth's magnetic field, generated by fluid motion in the planet's outer core, creates additional coupling between internal dynamics and rotational motion that affects long-term orbital evolution. Changes in the magnetic field reflect variations in core fluid motion that alter the angular momentum distribution within Earth's interior. The ongoing magnetic pole reversal, during which Earth's magnetic field weakens and reorganizes, may affect core dynamics in ways that influence rotational behavior and orbital coupling. Post-glacial rebound, the ongoing crustal uplift in regions previously covered by ice sheets, continues to redistribute mass within Earth's interior in ways that affect rotational dynamics. Scandinavia and northern Canada continue to rise at rates of several millimeters per year as the crust adjusts to the removal of ice sheet loads, while regions around the former ice margins subside correspondingly. These vertical crustal motions alter Earth's mass distribution and affect its rotational characteristics on timescales of thousands to tens of thousands of years. The challenge of incorporating Earth's changing shape into orbital calculations reflects the broader difficulty of coupling solid Earth geophysics with celestial mechanics across multiple time scales. Geological processes that affect Earth's mass distribution operate on timescales ranging from annual seasonal cycles to million-year tectonic processes. While their cumulative effects on orbital dynamics unfold over still longer periods that approach the age of the solar system itself, modern computational models of Earth's rotational dynamics include increasingly sophisticated representations of mass redistribution processes. Yet these models remain limited by incomplete knowledge of Earth's internal structure and the complex feedback mechanisms that link surface processes with deep interior dynamics, the mantle convection that drives plate tectonics, the core dynamics that generate Earth's magnetic field, and the climate processes that redistribute water and ice all affect Earth's shape and rotational behavior in ways that couple with orbital mechanics. Precision measurements of Earth's rotation reveal variations that occur on timescales ranging from hours to centuries, demonstrating the complexity of the processes that link Earth's changing shape with its motion through space. The International Earth Rotation and Reference System Service monitors these variations with atomic clock precision, providing data essential for accurate satellite navigation while revealing the subtle connections between Earth's internal dynamics and its orbital evolution. The study of Earth's changing shape and its effects on orbital motion illuminates the deep connections between planetary science disciplines that once seemed separate. Geophysics, atmospheric science, oceanography, and celestial mechanics converge in the problem of understanding how Earth's internal dynamics affect its motion through space, creating a scientific challenge that requires integration across multiple fields of study and timescales, spanning from human lifetimes to geological ages. Earth's orbital dance around the Sun follows three overlapping rhythmic patterns that astronomers call the Milankovitch cycles. Named after Serbian mathematician Milutin Milankovic, who calculated their periods and climate effects in the early 20th century. These cycles, changes in orbital eccentricity, axial obliquity, and the precession of the equinoxes, unfold over tens of thousands to hundreds of thousands of years, creating complex interactions that affect Earth's climate while contributing to the fundamental unpredictability of long-term orbital evolution. The eccentricity cycle, with its dominant period of approximately 100,000 years, describes how Earth's orbital path slowly changes shape from nearly circular to more elliptical and back again. During periods of high eccentricity, Earth's distance from the Sun varies by up to 18 million kilometers between perihelion and aphelion, creating significant differences in solar radiation received throughout the year. Currently, Earth's orbit exhibits relatively low eccentricity of 0.017, meaning our planet's distance from the Sun varies by only about 5 million kilometers annually. This eccentricity variation arises from gravitational perturbations by Jupiter, Saturn, and the other planets that slowly alter Earth's orbital shape through their combined gravitational influences. Computer calculations reveal that Earth's eccentricity oscillates between near zero and approximately 0.07 over periods that themselves vary due to the complex gravitational interactions among all solar system bodies. The irregularity of these variations reflects the chaotic nature of planetary gravitational dynamics that makes precise long-term orbital prediction impossible. The obliquity cycle, operating on a 41,000-year timescale, describes changes in Earth's axial tilt relative to its orbital plane, currently tilted at 23.5 degrees. Earth's axis oscillates between approximately 22.1 and 24, 5 degrees over this cycle, with the variation driven primarily by gravitational torques from the Sun and Moon acting on Earth's equatorial bulge. Greater obliquity creates more extreme seasonal contrasts, while reduced obliquity moderates seasonal temperature differences between summer and winter. Mars, lacking a large stabilizing satellite like Earth's moon, experiences far more dramatic obliquity variations that can reach 60 degrees or more, creating climate changes so extreme that the planet's polar ice caps can migrate to equatorial regions during periods of high obliquity. Earth's relatively stable obliquity reflects the Moon's gravitational influence, which acts as a cosmic gyroscope that resists changes to our planet's rotational axis. As the Moon slowly recedes from Earth, this stabilizing influence will gradually weaken, potentially allowing larger obliquity variations in the distant future. The precession cycles, with periods of approximately 19,000 and 23,000 years, describe how Earth's rotational axis slowly wobbles in space while maintaining its overall tilt angle. This wobbling motion, similar to a spinning top, causes the direction of axial tilt to change relative to Earth's orbital position, altering the timing of seasons relative to Earth's distance from the Sun. Currently, Earth reaches its closest approach to the Sun in early January, moderating northern hemisphere winters, but precession will gradually shift this timing over the coming millennia. The interaction among these three cycles creates complex patterns of climate forcing that have driven ice age cycles throughout Earth's history. Ice core records from Antarctica and Greenland preserve detailed evidence of these orbital influences on global climate, revealing how small changes in solar radiation distribution can trigger massive reorganizations of Earth's climate system. The mathematical relationships among the cycles create beating patterns where their effects sometimes reinforce each other and sometimes cancel out, producing the irregular timing of ice ages observed in the geological record. Modern climate models incorporate Milankovitch, forcing to understand past and future climate changes. Yet the complexity of interactions among orbital cycles, ice sheet dynamics, and atmospheric composition makes long-term climate prediction as challenging as orbital prediction itself. The climate system exhibits its own chaotic behavior that amplifies small orbital influences into large climate changes through feedback mechanisms involving ice albedo, vegetation patterns, and atmospheric greenhouse gas concentrations. The calculation of Milankovitch cycles requires precise knowledge of planetary masses, orbital parameters, and gravitational interactions that extends millions of years into the past and future. These calculations push the limits of computational celestial mechanics while revealing the fundamental connections between orbital dynamics and Earth's climate history. The accuracy of Milankovitch calculations decreases with increasing time due to the same chaotic dynamics that limit all long-term orbital predictions. Recent refinements to Milankovitch theory include the effects of orbital changes on tidal dissipation rates, which affect the Moon's recession and therefore Earth's rotational dynamics. The changing Earth-Moon distance alters tidal forces in ways that modify the efficiency of tidal energy dissipation, creating feedback effects between orbital evolution and climate forcing that operate over geological timescales. These coupled effects demonstrate how orbital mechanics and climate dynamics interact in ways too complex for simple linear analysis. The discovery of orbital cycles in ancient sedimentary rocks provides empirical confirmation of Milankovitch calculations, while revealing the deep time persistence of orbital influences on Earth's surface processes. Cyclic patterns in limestone formation, evaporite deposition, and other sedimentary processes preserve records of orbital forcing extending back hundreds of millions of years, offering glimpses into Earth's orbital behavior during geological periods when planetary configurations differed significantly from today. Astronomical observations of other planetary systems reveal that orbital cycles similar to Earth's Milankovitch patterns occur throughout the universe, suggesting that the complex interactions among planetary orbits, axial tilts, and climate represent fundamental features of planetary dynamics. The study of exoplanetary orbital evolution provides comparative context for understanding Earth's orbital cycles, while revealing the diversity of possible orbital behaviors in planetary systems with different masses and configurations. The Milankovitch cycles continue their ancient rhythms, slowly modifying Earth's orbital relationship with the Sun in ways that will influence our planet's climate for millions of years to come. These cycles operate with mathematical precision governed by celestial mechanics, yet their interactions create patterns too complex for perfect prediction, ensuring that Earth's orbital future contains elements of fundamental uncertainty that emerge from the deepest principles of gravitational dynamics and chaos theory. The mathematical heart of orbital prediction lies in what chaos theorists call sensitive dependence on initial conditions, a phenomenon where microscopic uncertainties in current measurements grow exponentially over time to create macroscopic unpredictability in future behavior. This fundamental characteristic of gravitational systems means that even perfect knowledge of physical laws cannot overcome the practical impossibility of measuring planetary positions and velocities with infinite precision. Current astronomical observations can determine Earth's position relative to the Sun with uncertainties of perhaps 10 meters, and its orbital velocity with uncertainties of millimeters per second. These measurement precisions represent extraordinary achievements in observational astronomy, yet they contain enough uncertainty to make Earth's orbital position completely unpredictable beyond time horizons of approximately 5 to 10 million years. The exponential growth of uncertainties ensures that prediction accuracy decreases by roughly 1 order of magnitude for each factor of 10 increase in prediction time. The mathematics underlying this exponential uncertainty growth emerges from the nonlinear nature of gravitational interactions among multiple bodies. In a system containing just 3 gravitating objects, small changes in initial positions can lead to dramatically different orbital outcomes through a process that mathematicians describe using Lyapunov exponents, numbers that quantify how rapidly nearby trajectories diverge from each other in phase space. For the solar system, these exponents indicate that uncertainties double approximately every few million years. Computer simulations of solar system evolution reveal the chaotic nature of planetary dynamics through statistical ensembles of orbital calculations that begin with slightly different initial conditions. These Monte Carlo simulations show that while most orbital outcomes remain relatively stable over billion-year timescales, a small percentage of trajectories lead to dramatic instabilities, including planetary collisions, ejections from the solar system, or complete orbital reorganization. The probability of such extreme outcomes increases with longer prediction times, reflecting the fundamental unpredictability embedded in gravitational dynamics. The challenge of initial condition sensitivity becomes particularly acute when attempting to incorporate all known solar system objects into orbital calculations. Each asteroid, comet, and planetary satellite adds additional gravitational influences that require precise initial position and velocity measurements. The cumulative effect of uncertainties in millions of object parameters creates a combinatorial explosion of possible future states that overwhelms even the most sophisticated computational approaches to orbital prediction. Modern numerical integration techniques used for orbital calculation must balance computational efficiency with accuracy requirements in ways that introduce additional sources of uncertainty. The finite time steps required for computer integration create discretization errors that accumulate over long integration periods, while round-off errors from finite precision arithmetic compound the problem further. These computational limitations ensure that even theoretical perfect knowledge of initial conditions could not yield perfect long-term orbital predictions using practical computational methods. The phenomenon of resonance overlap provides another mechanism through which small uncertainties can produce large orbital changes over extended time periods. When gravitational resonances between different planetary pairs begin to overlap in frequency space, The resulting dynamics can become chaotic even for systems that will remain stable if the resonance is operated independently. The solar system exhibits numerous such resonance overlaps that contribute to the long-term instability of orbital motion. Quantum mechanical uncertainty principles impose fundamental limits on the precision with which position and momentum can be simultaneously measured, creating theoretical constraints on orbital prediction accuracy that operate even in the absence of practical measurement limitations. While these quantum limits remain far below current observational capabilities for macroscopic objects like planets, they establish absolute boundaries on the precision of any conceivable future measurements, and therefore on the ultimate limits of orbital prediction. The concept of phase space, the mathematical framework in which orbital predictions unfold, provides geometric insight into why small uncertainties grow exponentially in gravitational systems. Each point in phase space represents a complete specification of all positions and velocities for every object in the system, and orbital evolution traces paths through this multidimensional space. The exponential divergence of nearby trajectories reflects the underlying geometry of phase space flows in gravitational systems. Historical studies of orbital prediction accuracy reveal how measurement improvements have paradoxically highlighted, rather than resolved, the fundamental limitations of long-term forecasting. Each generation of more precise astronomical observations has enabled more accurate short-term predictions, while revealing new sources of uncertainty that limit long-term predictability. This pattern suggests that improved measurement technology alone cannot overcome the intrinsic limitations imposed by chaotic dynamics. The practical implications of chaotic sensitivity extend beyond academic curiosity to affect real-world applications, including spacecraft navigation, asteroid impact assessment, and planetary defense strategies. Mission planners must account for exponentially growing uncertainties when designing long-duration space missions, while asteroid impact probability calculations must incorporate the fundamental unpredictability of long-term orbital evolution in their risk assessments. Modern research in orbital dynamics focuses on identifying timescales and parameter ranges where predictions remain reliable despite chaotic sensitivity. These investigations reveal that while detailed predictions become impossible over geological timescales, certain statistical properties of orbital motion may remain predictable over much longer periods. This distinction between detailed and statistical predictability offers hope for understanding long-term orbital evolution, even in the presence of deterministic chaos. The study of chaotic orbital dynamics connects celestial mechanics with broader areas of nonlinear science, revealing that similar mathematical structures appear in diverse physical systems ranging from weather patterns to quantum mechanical systems. This universality suggests that the limitations of orbital prediction reflect fundamental features of complex dynamical systems, rather than specific peculiarities of gravitational physics. The exponential growth of uncertainty in orbital systems serves as a humbling reminder that even the most precisely understood physical laws contain elements of fundamental unpredictability when applied to sufficiently complex systems over extended time periods. The mathematics of chaos theory ensures that perfect long-term orbital prediction remains impossible regardless of improvements in observational technology or computational power, establishing definitive limits on humanity's ability to forecast the gravitational future of our cosmic neighborhood. Beyond the familiar matter that composes stars, planets, and interstellar gas lies a vast reservoir of invisible mass that astronomers call dark matter, a mysterious form of matter that reveals itself only through its gravitational effects on visible objects, comprising approximately 85% of all matter in the universe. Dark matter creates gravitational influences that may subtly affect planetary orbits over cosmic timescales in ways that contribute to the fundamental unpredictability of long-term orbital evolution. Current observational evidence for dark matter comes primarily from galactic and cosmological scales, where its gravitational effects on star formation, galaxy rotation, and cosmic structure formation provide compelling evidence for its existence. The Milky Way galaxy contains roughly 5 times more dark matter than ordinary matter, distributed in a roughly spherical halo that extends far beyond the visible galactic disk. This dark matter distribution creates a gravitational environment that affects the motion of the entire solar system as it orbits the galactic center. The solar system travels through the galaxy at approximately 220 kilometers per second, completing one galactic orbit every 225 million years, a period astronomers call a cosmic year. During this galactic journey, the solar system encounters varying densities of dark matter that may create small but cumulative perturbations in planetary orbits through gravitational interactions. These perturbations operate over time scales much longer than typical planetary orbital periods, potentially contributing to long-term orbital evolution in ways that remain largely theoretical due to current limitations in dark matter detection. Local dark matter density near the solar system's current galactic position measures approximately 0.3 GeV per cubic centimeter, equivalent to roughly 1 proton mass per cubic centimeter of space. This seemingly negligible density becomes significant when integrated over the vast volumes relevant to planetary motion, potentially creating gravitational accelerations on the order of 10 circumflex 15 meters per second squared, forces far too small for direct detection but potentially measurable over million-year timescales through their cumulative effects on orbital evolution. The nature of dark matter remains one of the greatest mysteries in modern physics, with leading theoretical candidates including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. Each proposed form of dark matter would create different patterns of gravitational influence on solar system dynamics, with some models predicting detectable signatures in precise planetary orbit measurements, while others suggest effects too small for observation with any conceivable technology. Seasonal variations in Earth's velocity relative to the dark matter halo create time-varying gravitational environments that might affect planetary orbits in measurable ways. As Earth orbits the Sun, its velocity vector relative to the galactic dark matter halo changes by approximately 60 kilometers per second annually, potentially creating periodic variations in dark matter gravitational effects. These variations operate on annual timescales, but require centuries to millennia of integration time to produce orbital changes large enough for astronomical detection. The distribution of dark matter within the solar system itself remains highly uncertain, with theoretical models predicting anything from essentially uniform density to significant concentrations around massive objects like the Sun. Some theories suggest that dark matter might form bound structures called dark matter satellites that could create localized gravitational anomalies affecting planetary motion. Current observational limits constrain such structures to have masses smaller than Earth's moon. Yet even these limits allow for dark matter distributions that could affect long-term orbital stability. Experimental searches for dark matter particles using underground detectors, particle accelerators, and space-based instruments continue to place increasingly stringent limits on dark matter interaction strengths while failing to achieve direct detection. These null results constrain the properties of dark matter in ways that affect predictions for its gravitational influence on solar system dynamics, generally pushing theoretical models toward forms of dark matter that interact too weakly to create detectable orbital perturbations. The possibility that modified theories of gravity rather than dark matter explain galactic-scale gravitational anomalies introduces additional uncertainty into assessments of dark matter's influence on planetary orbits. Modified Newtonian dynamics, MOND, and other alternative gravity theories attempt to explain galactic rotation curves without invoking dark matter, predicting different patterns of gravitational influence on solar system scales that might affect long-term orbital evolution in ways distinguishable from standard dark matter models. Recent proposals suggest that dark matter might exhibit complex internal structure or undergo phase transitions that create time-varying gravitational environments affecting planetary motion. Some models predict that dark matter density could fluctuate on timescales relevant to orbital evolution, creating stochastic gravitational perturbations that contribute to the chaotic nature of long-term orbital prediction. These theoretical possibilities remain highly speculative, but illustrate how incomplete knowledge of dark matter properties affects assessments of orbital predictability. The search for dark matter signatures in solar system dynamics represents an active area of research that combines precision astrometry with theoretical physics. Proposed experiments include precision tracking of spacecraft trajectories, analysis of planetary ephemeris data, and searches for anomalous orbital precession that might reveal dark matter gravitational effects. Current observational precision remains several orders of magnitude away from detecting predicted dark matter influences, yet future improvements in measurement technology might eventually reveal these subtle gravitational signatures. The study of planetary motion in other stellar systems provides comparative context for understanding dark matter's potential influence on orbital dynamics. Exoplanetary systems embedded in different galactic environments may experience different dark matter densities and distributions, potentially revealing dark matter effects through statistical analysis of orbital properties across large samples of planetary systems. These comparative studies remain limited by current observational capabilities, but offer future prospects for detecting dark matter through its influence on planetary motion. The implications of dark matter for orbital prediction extend beyond direct gravitational effects to include its role in the broader cosmic environment that affects solar system evolution. Dark matter influences the formation and evolution of galactic structure, affecting the rate of stellar encounters, supernova explosions, and other galactic events that might perturb planetary orbits over cosmic timescales. The complex interplay between dark matter cosmology and solar system dynamics ensures that dark matter's influence on orbital prediction remains embedded in the broader challenge of understanding planetary motion within an evolving galactic context. The mystery of dark matter serves as a reminder that our understanding of the gravitational environment affecting planetary motion remains incomplete in fundamental ways. The possibility that 85% of the universe's matter exerts gravitational influences on planetary orbits through mechanisms still unknown to science introduces an element of epistemic uncertainty that extends beyond the mathematical chaos inherent in gravitational dynamics to encompass gaps in current physical knowledge. The Milky Way galaxy stretches across space as a vast spiral of stars, gas, and dark matter whose gravitational field reaches into every corner of the solar system with influences so subtle that they remained undetected until the precision of modern astronomy revealed their presence. This galactic gravitational environment creates what astronomers call tidal forces, differential gravitational accelerations that vary with position and orientation in ways that affect planetary orbits over cosmic timescales. The galactic tide arises because the Sun and planets experience slightly different gravitational accelerations from the galaxy's distributed mass, creating relative forces that tend to stretch and compress the solar system in directions aligned with the galactic gravitational field. These tidal accelerations measure approximately 10 circumflex 9 meters per second squared, forces so weak that they require millions of years to produce measurable effects on planetary motion, yet persistent enough to contribute to the long-term unpredictability of orbital evolution. The solar system's motion through the galaxy subjects it to time-varying tidal forces as our stellar neighborhood encounters different concentrations of galactic mass. The Sun oscillates vertically through the galactic disk with a period of approximately 60 million years, experiencing varying gravitational influences from spiral arms, star-forming regions, and dense molecular clouds. These encounters create episodic changes in the galactic tidal environment that may correlate with mass extinction events in Earth's fossil record through their effects on comet orbits and asteroid dynamics. Galactic rotation itself creates a shearing tidal field that affects the outer regions of the solar system most strongly. Objects in the Oort cloud, the spherical reservoir of comets that extends halfway to the nearest star, experience galactic tidal forces comparable to the Sun's gravitational influence at such enormous distances. These tidal perturbations can deflect comets from their distant orbits, sending them on long journeys toward the inner solar system, where they may affect planetary dynamics through gravitational encounters or impacts. The spiral structure of the Milky Way creates a time-varying gravitational environment as the solar system periodically crosses spiral arms during its 225 million year galactic orbit. Spiral arms contain enhanced concentrations of stars, gas, and dark matter that create stronger gravitational fields than the regions between arms. The solar system last crossed a major spiral arm approximately 13 million years ago, and will encounter the next arm in roughly 15 million years, potentially experiencing enhanced tidal forces during these crossings. Recent studies suggest that the galaxy's supermassive black hole, Sagittarius A*, may contribute to galactic tidal effects through its gravitational influence on the overall galactic mass distribution, located 26,000 light-years from the solar system. This 4 million solar mass black hole creates gravitational effects too weak for direct detection in planetary motion, yet its influence on galactic structure may affect the tidal environment in which the solar system evolves over cosmic timescales. The local group of galaxies, including the Milky Way, Andromeda, and several dozen smaller galaxies, creates an even larger scale gravitational environment that affects galactic motion and therefore the solar system's cosmic trajectory. The approaching collision between the Milky Way and Andromeda galaxies, predicted to occur in approximately 5 billion years, will dramatically restructure the galactic gravitational field and potentially affect solar system dynamics through enhanced tidal forces and gravitational interactions with stars from the merging galaxies. Galactic tidal forces exhibit directional asymmetries that affect different regions of the solar system in distinct ways. The tidal field stretches the solar system along the line connecting the galactic center with the solar system's current position, while compressing it in perpendicular directions. These directional effects may preferentially perturb planetary orbits with specific orientations relative to the galactic plane, potentially creating observable signatures of galactic influence in the statistical properties of solar system dynamics. The measurement of galactic tidal effects on solar system dynamics requires precision astrometry that approaches the fundamental limits of current observational technology. The European Space Agency's Gaia mission, designed to measure stellar positions with microarcsecond precision, may eventually detect galactic tidal signatures in the motion of distant solar system objects like trans-Neptunian objects and long-period comets. These measurements could provide empirical tests of galactic structure models while revealing new aspects of the cosmic environment affecting planetary motion. Computer simulations of solar system evolution that include galactic tidal effects reveal complex interactions between local planetary dynamics and the larger galactic environment. These simulations suggest that galactic tides may affect the long-term stability of planetary orbits through subtle perturbations that accumulate over hundreds of millions of years. The chaotic nature of planetary dynamics amplifies these tiny galactic influences in ways that contribute to the fundamental unpredictability of long-term orbital evolution. The study of other planetary systems within the galaxy provides comparative context for understanding galactic tidal effects on solar system dynamics. Planetary systems located in different galactic environments, such as globular clusters, the galactic bulge, or the sparse galactic halo, experience different tidal environments that may affect their orbital evolution in observable ways. These comparative studies remain limited by current exoplanet detection capabilities, but offer future prospects for understanding galactic influences on planetary motion. Galactic tidal forces interact with solar system dynamics through resonance mechanisms that can amplify small perturbations into larger orbital changes over extended time periods. The commensurability between galactic orbital periods and planetary precession rates creates potential resonance conditions where galactic tides could drive secular changes in planetary orbits. These resonances operate over time scales of tens to hundreds of millions of years, making their effects difficult to observe directly but potentially important for long-term orbital stability. The cosmic ray environment within the galaxy, influenced by supernova explosions and other high-energy phenomena, may create additional perturbations that affect solar system dynamics through electromagnetic forces and solar wind interactions. Variations in cosmic ray intensity during the solar system's galactic orbit could affect solar activity patterns and therefore the electromagnetic environment that influences planetary motion through radiation pressure and charged particle interactions. The dark matter distribution within the galactic halo creates gravitational effects that operate in conjunction with ordinary matter to produce the total galactic tidal field. Uncertainties in dark matter properties and distribution affect calculations of galactic tidal forces in ways that contribute to the unpredictability of their influence on solar system evolution. The complex interplay between dark matter cosmology and galactic dynamics ensures that galactic tidal effects remain embedded in broader uncertainties about the cosmic environment. The recognition of galactic tidal effects on solar system dynamics represents a relatively recent development in celestial mechanics that illustrates how expanding observational capabilities continue to reveal new sources of complexity in orbital prediction. Each improvement in measurement precision uncovers additional layers of gravitational influence that affect planetary motion, demonstrating that the problem of orbital prediction remains embedded in an ever-expanding web of cosmic interactions that extend from local planetary dynamics to the large-scale structure of the universe. The most powerful supercomputers on Earth, capable of performing quintillions of calculations per second, encounter fundamental mathematical limitations when attempting to predict planetary orbits with perfect precision over extended time periods. These computational constraints arise not from inadequate processing power, but from the inherent mathematical structure of gravitational dynamics, which requires infinite precision arithmetic to yield exact solutions for multi-body orbital problems. Modern orbital integration algorithms must discretize the continuous flow of time into finite computational steps, introducing truncation errors that accumulate with each iteration of the calculation. Even the most sophisticated numerical methods, designed to minimize these discretization effects, cannot eliminate them entirely when dealing with the nonlinear differential equations that govern gravitational motion. The cumulative effect of billions of computational steps required for million-year orbital integrations ensures that numerical errors eventually overwhelm the physical accuracy of any finite precision calculation. Floating point arithmetic, the mathematical foundation of computer calculations, represents real numbers using finite binary digits that introduce round-off errors in every operation. These errors, typically smaller than 1 part in 10 circumflex 15 for double precision calculations, seem negligible for individual computations but compound exponentially in chaotic dynamical systems like gravitational n-body problems. Over the millions of computational steps required for long-term orbital integration, round-off errors can grow to dominate the calculation and make results meaningless. The challenge of orbital computation becomes particularly acute when attempting to include all known solar system objects in a single, comprehensive calculation. The gravitational field of each asteroid, comet, and planetary satellite contributes to the forces acting on every other object, creating a computational problem that scales as the square of the number of included bodies. Including the million known asteroids larger than 1 kilometer in diameter would require roughly 10 circumflex 12 force calculations per timestep, pushing computational requirements beyond the capabilities of any conceivable computer. Variable time-step integration methods, designed to improve computational efficiency by taking smaller steps during close encounters and larger steps during quiescent periods, introduce additional complexities that affect long-term integration accuracy. The algorithms that determine optimal step sizes must balance competing demands for computational speed and numerical precision, often making choices that optimize short-term accuracy at the expense of long-term stability. These trade-offs ensure that even the most sophisticated adaptive integration schemes cannot achieve perfect long-term orbital prediction. Symplectic integration methods, specifically designed to conserve energy and angular momentum in Hamiltonian systems like gravitational dynamics, offer improved long-term stability compared to conventional integration techniques. However, these methods require computational step sizes small enough to resolve the shortest timescales in the problem, often making them prohibitively expensive for comprehensive solar system simulations that must track objects ranging from rapidly orbiting near-Earth asteroids to slowly precessing trans-Neptunian objects. The mathematical representation of planetary positions and velocities requires coordinate systems that introduce their own computational complexities and sources of numerical error. Cartesian coordinates, while conceptually simple, can suffer from numerical instabilities when dealing with highly eccentric orbits or close encounters between massive objects. Alternative coordinate systems, such as orbital elements or regularized variables, offer improved numerical behavior in specific circumstances, but require complex transformations that introduce additional computational overhead and potential sources of error. Modern supercomputers achieve their extraordinary computational speeds through parallel processing architectures that distribute calculations across thousands or millions of individual processors. However, gravitational n-body problems exhibit limited parallelizability because each object's motion depends on gravitational forces from all other objects, requiring extensive communication between processors that can limit the efficiency of parallel computation. This communication overhead becomes particularly problematic for the frequent small-time steps required for accurate orbital integration. Quantum computational approaches, still in their experimental infancy, offer theoretical possibilities for overcoming some classical computational limitations through quantum parallelism and other quantum mechanical effects. However, current quantum computers remain far from the stability and scale required for complex orbital calculations, and fundamental questions remain about whether quantum algorithms can provide exponential speed-ups for gravitational dynamics problems that appear to require inherently classical computational approaches. The verification of computational orbital predictions requires independent calculations using different algorithms, coordinate systems, and computational platforms to identify numerical errors and assess prediction reliability. These cross-verification studies consistently reveal that different computational approaches begin to diverge significantly after integration times of several million years, demonstrating that computational limitations rather than physical understanding limit the accuracy of long-term orbital predictions. Interval arithmetic and other rigorous computational methods attempt to track the propagation of numerical errors through orbital calculations by representing each computed quantity as an interval of possible values rather than a single number. These approaches can provide mathematically rigorous bounds on computational uncertainty, but they typically require orders of magnitude more computational resources than conventional methods, while often producing uncertainty bounds so large that they provide little useful information about orbital evolution. The development of specialized hardware for orbital computation, including graphics processing units and custom-designed astronomical computing engines, has improved computational capabilities for specific classes of orbital problems. However, these hardware advances cannot overcome the fundamental mathematical limitations imposed by finite precision arithmetic and the exponential growth of numerical errors in chaotic dynamical systems. Machine learning and artificial intelligence approaches to orbital prediction attempt to bypass traditional numerical integration by learning patterns in orbital motion from large datasets of computed or observed trajectories. These methods show promise for specific applications like asteroid trajectory, prediction over limited time horizons, but they cannot overcome the fundamental physical limitations imposed by chaotic dynamics and remain limited by the accuracy of the training data used to develop their predictive models. The study of computational limitations in orbital mechanics reveals fundamental connections between mathematics, computer science, and physics that extend beyond the specific problem of planetary motion. The impossibility of perfect long-term orbital prediction reflects deeper mathematical truths about computability, chaos theory, and the limits of numerical analysis that apply to a broad range of complex dynamical systems in science and engineering. Contemporary research in computational orbital dynamics focuses on developing probabilistic approaches that acknowledge fundamental limitations while providing useful statistical information about long-term orbital evolution. These methods attempt to characterize the probability distributions of possible future orbital states rather than predicting specific trajectories, offering a framework for understanding orbital evolution that accepts uncertainty as an intrinsic feature rather than a computational failure. The computational challenge of orbital prediction serves as a humbling reminder that even unlimited computational resources cannot overcome the mathematical limitations imposed by chaos theory and finite precision arithmetic. The most powerful computers imaginable, operating for cosmic ages, would eventually encounter the same fundamental barriers that limit current orbital predictions, ensuring that perfect long-term orbital forecasting remains impossible regardless of technological advances. Time itself becomes the ultimate adversary in the quest for orbital prediction, transforming apparent precision into exponential uncertainty through mechanisms that operate with mathematical inevitability across the vast scales of cosmic evolution. The erosion of predictive accuracy with increasing time horizons reflects not inadequate knowledge or computational limitations, but fundamental features of gravitational dynamics that ensure perfect long-term orbital forecasting remains impossible regardless of technological advancement. Current astronomical observations can determine Earth's position with uncertainties of perhaps 10 meters and predict its location 1 week hence with similar precision. Extending the prediction horizon to 1 month introduces uncertainties of hundreds of meters, while 1-year predictions carry kilometer-scale margins of error. This pattern of exponentially growing uncertainty continues relentlessly. 10 years brings uncertainties of hundreds of kilometers. 1 century expands errors to thousands of kilometers. And 1 millennium makes Earth's predicted position uncertain by distances exceeding the planet's orbital circumference. The mathematics underlying this temporal degradation of prediction accuracy emerges from the sensitive dependence on initial conditions that characterizes chaotic dynamical systems. Small uncertainties in current measurements double approximately every 5 million years for Earth's orbital motion, creating prediction horizons beyond which detailed forecasts become meaningless. This doubling time, called the Lyapunov time, represents a fundamental timescale that governs the transition from predictable to unpredictable behavior in gravitational systems. Different solar system objects exhibit different characteristic timescales for the onset of unpredictability, with smaller bodies generally becoming chaotic more rapidly than massive planets due to their greater susceptibility to gravitational perturbations. Asteroid orbits become unpredictable over time, scales of thousands to millions of years, while the giant planets maintain some degree of predictability over hundreds of millions of years. These varying timescales reflect the complex hierarchy of gravitational influences that govern solar system dynamics. The concept of prediction horizons extends beyond mathematical abstractions to affect practical applications including spacecraft mission planning, asteroid impact assessment, and planetary defense strategies. NASA and other space agencies must account for exponentially growing uncertainties when designing long-duration missions to outer planets. While asteroid impact probability calculations become increasingly uncertain as prediction times extend beyond several centuries, these practical limitations reflect the fundamental timescales that govern predictability in gravitational systems. Historical studies of orbital prediction accuracy reveal how each generation of improved observations has simultaneously extended short-term prediction capabilities while highlighting the fundamental limitations of long-term forecasting. Ancient Babylonian astronomers could predict lunar eclipses decades in advance using simple mathematical patterns, while modern astronomy achieves century-scale predictions for planetary positions. Yet both ancient and modern approaches encounter the same exponential degradation of accuracy that makes thousand-year predictions essentially impossible. The interaction between multiple timescales in solar system dynamics creates complex patterns of predictability that vary with the specific orbital characteristics being forecast. Planetary positions become unpredictable over shorter timescales than orbital periods, while certain statistical properties of orbital motion may remain predictable over much longer periods than detailed trajectories. This hierarchy of predictability reflects the different mathematical structures that govern various aspects of gravitational dynamics. Resonance phenomena create additional complications for time-dependent prediction accuracy by introducing sudden transitions between different dynamical regimes over time, scales that may be shorter or longer than typical prediction horizons. Objects caught in gravitational resonances may exhibit apparently stable behavior for millions of years before undergoing rapid orbital changes that fundamentally alter their future evolution. These sudden transitions make it impossible to predict when current orbital patterns will break down, even when the general trend toward chaos is well understood. The study of orbital prediction accuracy over geological timescales reveals connections between celestial mechanics and Earth's climate history through orbital influences on ice age cycles and other climate phenomena. Ice core records and other paleoclimatic data provide empirical tests of orbital calculations extending back hundreds of thousands of years, generally confirming theoretical predictions while revealing subtle discrepancies that may reflect the cumulative effects of chaotic dynamics or incomplete knowledge of past solar system configuration. Quantum mechanical considerations introduce fundamental limits on measurement precision that establish absolute bounds on prediction accuracy, even in the hypothetical absence of classical chaos. The uncertainty principle limits the precision with which position and momentum can be simultaneously measured, creating quantum mechanical noise floors below which no conceivable measurement technology can penetrate. While these quantum limits remain far below current observational capabilities for macroscopic objects like planets, they establish theoretical boundaries on the ultimate precision of orbital prediction. The development of statistical approaches to orbital prediction acknowledges the fundamental limitations of deterministic forecasting while providing useful probabilistic information about long-term orbital evolution. Monte Carlo methods generate ensembles of possible orbital futures by propagating uncertainties through gravitational calculations, producing probability distributions that characterize the range of possible outcomes rather than predicting specific trajectories. These statistical approaches offer the most realistic framework for understanding orbital evolution over extended time periods. Modern research in orbital dynamics focuses on identifying the most robust features of long-term orbital evolution, those statistical properties and dynamical patterns that remain predictable despite the chaos that destroys detailed trajectory forecasts. The search for such invariant structures in phase space represents an attempt to salvage useful information about orbital evolution from the fundamental unpredictability that characterizes detailed motion over cosmic timescales. The philosophical implications of time-dependent uncertainty in orbital prediction extend beyond practical astronomy to touch fundamental questions about determinism, predictability, and the nature of physical law. Orbital motion represents one of the most successfully understood phenomena in physics, governed by mathematical laws that have been tested with extraordinary precision. Yet even this paradigmatic example of scientific success encounters absolute limits on predictability that reflect deep features of mathematical reality. Climate models attempting to incorporate orbital forcing over geological timescales must confront similar limitations. As the orbital cycles that drive ice age patterns become increasingly uncertain over the million-year timescales relevant to long-term climate evolution, the coupling between orbital mechanics and climate dynamics creates additional feedback mechanisms that compound the uncertainty in both orbital and climate predictions over extended time periods. The recognition that time itself imposes fundamental limits on orbital prediction represents a mature acceptance of the boundaries of scientific knowledge that distinguishes modern understanding from earlier hopes for complete predictability in physical systems. This acceptance does not diminish the value of orbital mechanics, but rather places it within a broader framework that acknowledges uncertainty as an intrinsic feature of complex dynamical systems, rather than a temporary limitation to be overcome by improved technology or understanding. The cosmic dance continues with eternal patience, each celestial body following gravitational laws with perfect precision, while participating in interactions too complex for complete prediction across the vast timescales of cosmic evolution. Earth maintains its steady progress around the Sun, completing each annual orbit with familiar regularity while slowly, imperceptibly, participating in gravitational exchanges that will reshape its orbital characteristics over millions of years in ways that no computational power can foresee with certainty. The irony of orbital mechanics lies in this paradox between local predictability and global uncertainty. The same mathematical laws that allow astronomers to calculate planetary positions with extraordinary precision over human timescales also guarantee that such precision must inevitably decay over cosmic timescales through the amplification of microscopic uncertainties into macroscopic unpredictability. This mathematical inevitability reflects not failure of scientific understanding, but rather deep insights into the nature of complex dynamical systems that operate throughout the physical universe. Jupiter continues its stately progress through the outer solar system, its massive presence creating gravitational currents that flow through space with patient persistence, while its own orbital evolution remains coupled to Saturn, Uranus, and Neptune in ways that ensure the gas giant's future influence on Earth cannot be calculated with perfect accuracy. The great planet's gravitational field reaches across hundreds of millions of miles to touch Earth's orbital motion, with forces too small for immediate detection, yet large enough to accumulate across geological time into orbital changes that exceed the precision of any conceivable prediction. The Moon drifts silently away from Earth at its steady pace, each night moving imperceptibly farther into space while gradually weakening the gravitational embrace that has shaped both worlds for billions of years. This ancient recession continues its slow modification of Earth's orbital dynamics, introducing changes that unfold over time, scales so vast that human civilization represents but a fleeting moment in the lunar retreat that will eventually transform the Earth-Moon system beyond recognition. The tidal forces that drive this separation operate with clockwork precision, while ensuring that Earth's future orbital evolution contains elements of fundamental unpredictability. Venus and Mercury race through their inner orbital paths, creating high-frequency gravitational perturbations that ripple outward through the solar system in patterns too complex for analytical solution. These inner worlds participate in gravitational resonances and chaotic interactions that demonstrate how even the most fundamental physical processes become unpredictable when multiple influences combine across extended time periods. Their rapid orbital motion creates the shortest timescales in planetary dynamics, while contributing to the longest-term uncertainties in orbital prediction. The asteroid belt maintains its ancient structure. Millions of rocky fragments following individual elliptical paths while collectively creating gravitational influences that affect planetary motion through mechanisms that span from classical perturbation theory to modern chaos theory. Each asteroid contributes its microscopic gravitational voice to the cosmic chorus, while the belt as a whole undergoes slow evolution driven by collisions, resonances, and gravitational migrations that will alter its mass distribution in ways that cannot be predicted with certainty. Solar wind continues to flow outward from the Sun, carrying charged particles and magnetic fields through the solar system, while creating electromagnetic forces that interact with planetary magnetospheres in ways that affect orbital dynamics over cosmic timescales. The Sun's variable output creates corresponding changes in these electromagnetic influences, introducing additional time-dependent perturbations that contribute to the web of interactions, making long-term orbital prediction impossible. The solar wind represents the dynamic nature of the supposedly constant Sun, revealing that even the central gravitational anchor of the solar system participates in changes that affect orbital evolution. Relativistic effects continue their subtle modification of planetary motion, causing orbits to precess slowly through space while demonstrating how even the most successful physical theories contain mathematical complexities that limit long-term predictability. Einstein's insights into the nature of gravity reveal connections between orbital mechanics and the fundamental structure of space-time that extend orbital prediction beyond classical physics into realms where quantum mechanics and general relativity intersect in ways that remain incompletely understood. The galactic environment maintains its patient influence on solar system dynamics, creating tidal forces so weak that they require millions of years to produce measurable effects, yet persistent enough to contribute to the long-term orbital evolution of planets and smaller bodies. The Milky Way's rotation carries the solar system through varying gravitational environments that affect the Oort cloud and outer solar system in ways that may influence inner planet dynamics through complex chains of gravitational interaction extending across astronomical distances. Dark matter remains hidden throughout the galaxy, its gravitational influences operating through mechanisms still unknown to science, while potentially affecting planetary orbits in ways too subtle for current detection, yet significant enough to contribute to the fundamental uncertainty that characterizes long-term orbital prediction. The mysterious nature of dark matter ensures that orbital mechanics remains embedded in broader cosmological questions that connect planetary motion with the deepest unsolved problems in fundamental physics. Computational limitations ensure that even unlimited technological advancement cannot overcome the mathematical barriers that prevent perfect long-term orbital prediction. While chaos theory provides the mathematical framework for understanding why such limitations represent fundamental features of gravitational dynamics, rather than temporary obstacles to be overcome, the exponential growth of uncertainty in chaotic systems creates prediction horizons beyond which detailed forecasts become meaningless, regardless of computational power or observational precision. Time itself emerges as the ultimate limitation on orbital prediction, transforming apparent precision into exponential uncertainty through mechanisms that operate with mathematical inevitability across cosmic timescales. The temporal degradation of prediction accuracy reflects the deep connection between orbital mechanics and chaos theory, revealing that even the most successfully understood phenomena in physics contain elements of fundamental unpredictability that emerge over sufficiently extended time periods. The recognition of these limitations represents not failure, but rather mature wisdom about the boundaries of scientific knowledge and the nature of complex physical systems. Orbital mechanics achieves extraordinary success in its domain of applicability, while acknowledging that perfect long-term prediction remains impossible due to mathematical principles that extend far beyond the specific problem of planetary motion to encompass broad classes of dynamical systems throughout the natural world. Earth continues its ancient journey around the Sun, following gravitational laws with mathematical precision, while participating in cosmic interactions too complex for complete understanding. The planet maintains its life-supporting orbit through the delicate balance of forces that have operated for billions of years, ensuring stability over time scales relevant to biological evolution while containing seeds of change that will slowly, inexorably, alter its path through space in ways that demonstrate both the power and limitations of scientific prediction. The cosmic dance slows to a whisper, celestial bodies drifting through their eternal choreography as the mathematics of prediction dissolves into the deeper mystery of time itself. Earth spins gently through space, carrying its cargo of life around the familiar path that has sustained our world for billions of years, while slowly, imperceptibly, participating in gravitational exchanges that stretch beyond the boundaries of complete knowledge. The paradox settles into stillness, perfect laws governing imperfect prediction, mathematical precision yielding to cosmic uncertainty, the clockwork universe revealing its deeper chaotic heart. Each planet follows its gravitational destiny with unwavering accuracy, while the whole system drifts toward a future that no computation can fully capture. No theory can completely illuminate. Uncertainty becomes not failure but wisdom. Chaos not disorder but the deeper order that emerges when infinite complexity meets finite understanding. The orbital paths continue their ancient rhythms, writing equations in space and time that speak of forces too vast for human comprehension, patterns too complex for perfect prediction, beauty too profound for complete capture in mathematical symbols. Jupiter maintains its distant watch, Venus traces her inner spirals, Mercury races through solar fire, while the moon retreats into darkness with patience measured in cosmic ages. The asteroid belt continues its slow evolution. Solar wind carries stellar breath across impossible distances, and dark matter whispers through galactic space, with gravitational voices too quiet for direct detection, yet persistent enough to shape the cosmic architecture in which our small world spins. The dance continues without audience, without purpose beyond the pure expression of physical law. While prediction fades into probability and certainty, dissolves into the vast uncertainty that cradles all knowledge. In this dissolution lies not defeat but the recognition that some questions exceed the boundaries of answerable inquiry. Some futures remain forever beyond the reach of any conceivable calculation. Earth drifts through its orbit with the quiet confidence of 4 billion years, following the same gravitational principles that govern galaxies and atoms, while carrying within its motion the seeds of changes too subtle for prediction, too distant for concern, too beautiful for anything but acceptance of the cosmic mystery that holds our world in its gravitational embrace. The orbit continues, its future unknowable, its present perfect, its past a testament to the patient forces that shape worlds across timescales beyond human imagination. In this continuing mystery lies the deepest truth about the motion of planets, that even perfect understanding contains perfect uncertainty. And in that uncertainty rests the infinite possibility that makes the cosmos not a machine but a living expression of mathematical beauty, too vast for complete comprehension. Sleep comes to the cosmic dance as it comes to all things, not as ending but as the quiet acceptance of mystery, the peaceful recognition that some questions find their answer not in prediction but in the eternal present moment where Earth spins through space, following laws too perfect for complete prediction, too beautiful for anything but wonder.